Hello, I'm McHale from the University of Edinburgh, and I'd like to talk about my work on complex non-Newtonian suspensions. I'm going to start with the bold claim that we can model any pure granular suspensions flow with a single model, which is constraint theory, and this is a mean field framework by which friction and adhesion reduce the degrees of freedom of particle-particle pairs, and this means we can model any flow curve as a fraction of frictional and adhesive contacts, which gives you a complex stress-dependent jamming volume fraction. And as we know from White-Cates theory, the viscosity of a suspension depends on the distance between your volume fraction and your jamming volume fraction, and you get jamming when these cross. So what can we do with this? Well, I have a silica suspension, which is a granular suspension that can be tuned between multiple rheologies via the addition of the anionic surfactant SDS, shown in section 3, where we have yield stress dominated flow in the red and the yellow curves, all the way down to thickening dominated curves in the pink with intermediate flow curves. And the dashed lines here are direct fits to constraint theory. And in fact, the graphs in section 2 correspond to the uppermost graphs on this from this data. And we can pull the critical stresses for the formation of frictional contacts and the breaking of adhesive contacts from this. And in fact, what we see is that there's a heavy reduction in the onset stress for the breakdown of adhesive contacts with surfactant, but there's very little effect that the surfactant has on the formation of frictional contacts. But we don't actually expect this, because as we add surfactant to the surface of the particles, we're increasing the repulsive force between the particles that has to be overcome to cause frictional contact, and therefore we expect this sigma star to increase, but we don't see that. So how could we explain that? This could be explained by patchy particle theory, where the particles have heterogeneous surface chemistry, and therefore it's localized areas of the particles that cause this adhesion and therefore yield stress. And this has been directly analyzed by the use of EDS, which is an elemental composition analysis technique you can do during electron microscopy. And this is shown in section 4, with the red areas of the lines on the electron image corresponding to areas that move away from the expected 2:1 oxygen to silicon ratio, which doesn't correspond to any particular type of silica. And in fact, this does correspond to hydrophobic silane patches, which would cause adhesion and therefore yield stress. So overall, we've been able to analyze these suspensions from the bulk flow to the particle interactions to the elemental chemistry that informs these other aspects. And this can be expanded from quartz flower to any suspension in terms of both the application of constraint theory and the integration of other analysis techniques. This allows you to control the formulation of any suspension to give you the desired rheology. Thank you very much.